Section 7.8, Factoring Polynomials Completely. So far we've looked at lots of different methods to factor polynomials. The first thing that we want to look for all the time is a greatest common factor. That's always our first step. From there, we think about some other options. We look to see if we have a difference of squares, something that's in the form of a squared minus b squared. If it's not a difference of squares, we would check to see if it's a trinomial where the lead coefficient is 1. If it's in the form of x squared plus bx plus c, we try to figure out the two numbers that multiply to c and add up to b and use those to factor our polynomial. Maybe we're not as lucky, and after looking for a GCF, we have a trinomial that's in the form of ax squared plus bx plus c. Lead coefficient is not 1. In this case, use the box method, the Punnett square method, in order to try to factor this polynomial. And finally, we have a method we're going to talk about today, which is a grouping method, which is commonly used if we actually have 4 or more terms in our polynomial. It's actually something that we basically used in the Punnett square method with the trinomials where a does not equal 1. But we're just going to look at it a little bit differently today. So no matter what, always look for a GCF first and then try one of your other 4 methods in order to factor a polynomial completely. Here we have a polynomial with 4 terms. And one thing that we're going to try to do anytime we have 4 terms is what we call the grouping method. If I look at these first 2 terms, x cubed and 3x squared, I notice that they have something in common. They have a common factor of x squared. If I look at the next two, the 2x and the plus 6, they have a common factor of 2. There's no greatest common factor between the 4 terms, but I can group them into pairs because each set of pairs has common factors. If I look at the first set having a common factor of x squared, I want to factor just those 2 terms. And I'm going to have x squared times, well, x squared times something is x cubed, that's x, and x squared times something is 3x squared, that's a positive 3. Again, just to make sure that I've done this correctly, you can distribute your x squared to your binomial, and you'll end up getting the first 2 terms up here. Repeat this process with the next two. 2x and 6 both share a positive 2, so I'm going to put a positive 2 there. And when I think about what would have to go in parentheses now, I say 2 times something is 2x. Well, that's going to be x. And 2 times something is 6. That's plus 3. So what I've done here is I've looked at taking a common factor out of 2 different pairs of terms from my original polynomial. And when I did that, I'm left with something special in parentheses. Both of these contain an x plus 3. So what I'm basically going to do is I'm going to treat this whole block of x plus 3 as a common factor of 2 terms. The x squared times x plus 3 and the 2 times x plus 3. And so I take x plus 3 and I'm going to factor that GCF as a binomial factor out of my polynomial. What that leaves me with is, well, x plus 3 times something gives me x squared times x plus 3. Well, that something then has to be the x squared that I started with right here. Similarly, this term, 2 times x plus 3, comes from x plus 3 times something. That something is the 2 that's left behind. And there I have my factored form. X plus 3 times x squared plus 2 is completely factored. Anytime that I have an x squared plus a number, it's going to be prime. The only time I'll be able to factor it is if it's x squared minus a perfect square. So since 2 is not a perfect square and it's being added, it definitely doesn't work here. A quick FOIL will confirm that this works. X times x squared is x cubed. X times 2 is 2x. 3 times x squared is a positive 3x squared. And 3 times 2 is a positive 6. If I was to rewrite that in standard form, you'd see that it's exactly the same as what I started with. So that's the grouping method. First, group the terms that have common factors. Then factor out the GCF of each pair of terms, leaving behind a binomial. They need to be the same. And then factor that common binomial as a factor and leave behind the x squared plus 2 that's the result of the factoring. Check your work and you'll be good to go. Let's see an example right here where we have to do a little bit of work first. If I try to separate these into two different groups, I have x squared and y and x and xy. Well, x and xy, the second pair, do have something in common. They share an x. But the first group doesn't have anything in common. And so that's going to be problematic because if I just kind of leave them in these groups where it's x squared plus y and then x 1 plus y, I don't have the same binomial factor here. So I'm not going to be able to proceed any further. That's not going to work. Instead, what I have to do is I have to move things around so that then I can apply the grouping method. I only have 2 terms that contain a y, so maybe I can maneuver those so that they're next to each other. I'm going to switch around the x and y that are in the middle there and get x squared plus x plus y plus xy. I'm just switching around the order like that now. It's the same statement, just rearranged. Now I want to group with these 2 pairs. The x squared and the x have an x in common, and that would leave behind an x plus 1. Let's do a distributive property to double check that. Y and x plus y have a y in common, and it's positive, so I'm going to make it a plus y, and that would leave behind 1 plus x. Well, it looks like my binomials are a little bit different. I have x plus 1, and I have 1 plus x. Now, while they look different, they actually are identical. They're identical because I could rewrite one as the other. X plus 1 is the same thing as 1 plus x. So I could change my second one to just be x plus 1 times y. And now that they're the same, I have a common binomial factor. I'm going to take those out, and I'm going to have x plus 1. And then what gets left behind is the x and the plus y. And that's all that I need to fully factor this polynomial. That's the grouping method. We put them in an order that made me so that I could group them with common factors, remove the common factor from each pair, get a common binomial factor, put that in front, and then leave behind the coefficients of that binomial factor. And there you go. Here are 2 problems for you to try. Pause the video, do the work, and then restart the video to check how you did. Now it's time to reveal the answers. And there you have it. One thing I just wanted to point out is that in the first example, although a and 3 don't have a common factor, we could treat 1 as a common factor, and that's going to be clear when we take the a squared out of my first 2 terms, and it leaves me with a plus 3. So I want to make sure that I get an a plus 3 here, and that's a way to guarantee that it will work. So you have to make sure you have a plus 1 there, otherwise we won't get the a squared plus 1 correct. Also, a squared plus 1, even though a squared and 1 are both perfect squares, because it's an addition, it's not factorable. If it was a squared minus 1, I could factor it once more, making it a difference of squares. But in this case, I cannot because it's a squared plus 1. And in the second example, just had some rearranging to do. I switched the 2 middle terms so that I could group a little bit more efficiently. And then I recognized that y plus x is equal to x plus y, so that I had a common binomial factor. And I went from there. You also could switch the order of these. You could have y plus 2 times x plus y, or if it's addition, you can move things around. You've got some options, but that's what you need to do in order to factor completely using the grouping method. Just wanted to warn you about what can happen with negatives. It's just something you have to be careful about. If I have h cubed plus 4h squared minus 25h minus 100, what I want to do here is I want to group, looking at my two pairs there, the first two share an h squared, which would leave behind h plus 4. And now what I want to make sure I do is I want to leave behind an h plus 4 in my second set of factors here, my second term. So I think, how do I transform negative 25h into h? Well, I'd have to take out of that a negative 25. And that's going to leave the h there. I just have to make sure that this is actually going to work, because if I take out a negative 25, I'm also taking a negative 25 out of negative 100. That's what allows it to become plus 4. And so I have h squared times h plus 4 minus 25 times h plus 4. At this point I have a common binomial factor of h plus 4. And so then that's going to leave me with h squared minus 25. Now at this point I might think that I'm done, but I actually have to realize that this second factor is a difference of squares. It's h squared minus 25, which is 5 squared. So I can use my special product and factor that further, keep my h plus 4, and make this h plus 5, h minus 5. If you don't do that part, it's not fully factored. It's factored, but just not completely. So you got to make sure that you're always double checking to see if you can factor anything further once you get going. But just be careful with negatives. Make sure that you apply all the rules to make sure that it's still adding up and multiplying the correct way. Now it's time to put all of our tools together and just be given a polynomial and be told, factor it completely. Anytime that's the case, the first thing we always look for, never forget it, is the GCF. Looking at my first example, I check this trinomial and say, do all three of my terms share a common factor? In terms of the coefficients, they share a 3, and in terms of the x's, they each share an x. So when I take that 3x, which I'm going to have to make sure I include the whole way through, that's going to leave behind an x squared plus 2x minus 6. A quick distributive property will make sure that we have done that correctly. 3x times x squared is 3x cubed, 3x times 2x is 6x squared, and 3x times negative 6 is negative 18x. So now I have to make sure that I can factor no further. If I have no more exponents, I can't factor 3x any further, so I just would be trying to factor this trinomial. Now, because my lead coefficient is 1, I know that I'm basically just using the puzzle with the addition and multiplication problems. And I'm looking to come up with two numbers that are going to multiply to my constant of negative 6, and two numbers that are going to add up to my coefficient of x, which is 2. Well, since I'm multiplying to get a negative 6, I know I'm going to have one positive number and one negative number. And the only ways to multiply and get 6 are 1 and 6, and 2 and 3. But any combination of those is not going to add up to 2 when one of those numbers is positive, one's negative. It's either going to add up to 5, negative 5, or 1 or negative 1. So there's no way to break it down any further. Individually, this trinomial is prime. That means that this is my fully factored form. It does not mean that my original polynomial is prime, because I could write it as 3x times x squared plus 2x minus 6. But it does mean that my resulting trinomial factor is prime. Let's look at the next example. Again, look for a common factor first. If I look at this common factor first, I'm going to see that it has a 7 and an x squared as a common factor, which would leave behind x squared minus 4. Can't break down a monomial any further, 7x squared. X squared minus 4 I actually can break down, and that's going to be a difference of squares. So that allows me to quickly jump to 7x squared, x plus 2, x minus 2, because x to the second power is x squared, and 2 to the second power is 4. Now, quick note on this one. Let's say we didn't notice the x squareds at first as a common factor, and we'd only taken out a 7. So instead of doing that, we said 7, and then that kept it as x to the fourth minus 4x squared. Well, at that point, what you would have found is that x to the fourth could be written as x squared squared, and 4x could be written as 2x squared. Sorry, that's 4x squared. Once again, that's a difference of squares. That would be 7 times x squared minus 2x, or plus 2x, and then x squared minus 2x. Then, from each of these, we'd have a common factor of an x, and that's where we would end up getting 7 times x, and leave behind x plus 2, x minus 2, which would eventually bring us back to my answer. Certainly that way is more convoluted, but if we don't pick the right way to factor it at first, we can always get where we need to go as long as we continue to factor completely. And so that's what you would need to do there. All right, let's move on. Here are 3 examples for you to try. Make sure you factor these polynomials completely after pausing the video, and then turn it back on to check your work. All right, let's see the answers. So how'd you do? Did you make sure to look for a common factor first? Because you had one in the first 2 examples. Actually, in all 3, even though you didn't have a coefficient of the m cubed. In the second example, you could write it out as y minus 3 times y minus 3 instead of y minus 3 squared, but you could recognize that that's a special product and immediately jump there, or use the puzzle method. If we happen to have a lead coefficient other than 1, make sure that you use the Punnett square method, or whatever it takes, trial and error, guess and check, to factor these completely. All right, hope you did well.